In our previous video, we discussed the electric field. Now I want to go deeper into the electric field in preparation to understand the Mosfet transistor that we'll be talking about in the next videos. Now on the right, we have a mass that is above the Earth. Now we're all familiar with the gravitational field. So here we have the ground, or the Earth, and if we hold a mass or a rock up in the air, we know that the Earth exerts a force on this mass that tends to pull it towards the center of the Earth. Now a similar thing exists with an electric field. If, for example, we have two metal plates, and this upper plate will put a positive charge, and on the bottom plate we'll put a corresponding negative charge. When we do that, we create what is called an electric field, or an E field, that points in this direction, just like the gravitational field points towards the Earth. The electric field points from the positive plate to the negative plate. Now, in the Earth's gravitational field, the force is exerted on a mass. But in the electric field, the force is exerted on a charge. And we'll call this charge Q sub 0. And this is generally a very tiny charge, because if this charge was very big, it would influence this electric field. Just like if this mass was extremely large. If it were the mass of the moon, it would change the field at the surface of the Earth. So we always assume that this mass is rather small compared to the mass of the Earth, just as this charge Q0 is relatively small compared to these surrounding charges on these metal plates. So if we write an equation for this electric field, I'll call it E for electric field. This electric field is equal to the force on this small charge, which we'll call Q0. And force is in the units of newtons, and charge is in the unit of coulombs. And this is also equal to the units of volts per meter. So a newton per coulomb is equivalent to a volt per meter. So let's not use newtons per coulomb, just think in terms of volts per meter. Now this force F is the force on the small charge. And if this is a positive charge, Q0 is a positive charge, the force is in the direction of this electric field. The electric field tells us the direction of the force if we put a small positive charge into this field. So volts per meter, let's investigate what that really means. So let's redraw our metal plates. So we have a top plate with a positive charge, and we have a bottom plate with a negative charge. We put a tiny point charge, Q0. That's a positive charge. Now we know that positive charges, or like charges, repel each other. So this Q0 will be repelled by the positive charges at the top and attracted to the negative charges at the bottom. So we know that the electric field is in this direction. Now, we said that the electric field is measured in volts per meter. So let's assume that the distance between these plates is 1 meter. And let's presume that we have a voltmeter that I'll call V, and we measure the voltage from this negative plate to the positive plate. And let's presume that we measure 1 volt. In this case, the electric field is equal to 1 volt per meter. Let's say that I want to make this electric field stronger. How can I do that? One way I could do that is I could space these plates closer to each other. And let's presume I have the same charge. So this distance now, let's say, is a half a meter. And my voltage is still 1 volt. In this case, the electric field has increased. It is equal to 1 volt divided by 1/2 of a meter, which is equal to 2 volts per meter. Now, if I wanted to increase the electric field even more, I could add more charge, and I could increase this voltage from 1 volt to 2 volts. In this case, I'd have an electric field that would be 2 volts divided by 1/2 of a meter, or 4 volts per meter. So let's investigate this electric field and the effect that it has on the Mosfet transistor. From the previous video, recall that the Mosfet transistor has a gate electrode, and below the gate electrode is an insulating material, and below this insulating material is silicon. Let's presume that we diffuse in a region here. This is an N-type region, this is an N-type region, and our wafer is composed of a P-type region. So if we put a voltage, positive voltage, on this gate electrode relative to these N regions, so if I have a voltmeter between this N region and this gate, I measure a voltage, perhaps it's 1 volt or 2 volts or 4 volts. Let's presume that these N regions are at a ground potential. This is both at ground. And when we apply a voltage to this gate electrode, we develop an electric field below the gate. And this electric field has an effect on the region below the gate. Now, the thinner I can make this insulating material, the thinner this dimension, that I'll call T-ox for the thickness of this oxide layer. The thinner or the smaller T-ox, the greater this electric field. And the higher the voltage, if I go to 4 volts, the stronger the electric field. So a 4 volt will be stronger than a 1 volt. It will produce a stronger electric field. And as this electric field is increased, the region at the surface of the wafer in this region is affected. And recall that the electric field is the force on a positive charge, or a hole. So these holes are forced down, and electrons or negative charge is forced to the surface. It is attracted by this electric field, and we change the conduction of this region under the electrode, and that produces a transistor action from this N region to this other N region. And we'll discuss that further in our next video. Thing exists with an electric field. If, for example, we have two metal plates, and this upper plate we put a positive charge, and on the bottom, in our previous video, we discussed the electric field. Now I want to go deeper into the electric field in preparation to understand the Mosfet transistor that we'll be talking about in the next videos. Now on the right, we have a mass. Hold a mass or a rock up in the air. We know that the Earth exerts a force on this mass that tends to pull it towards the center of the Earth. Now a similar thing that is above the Earth. Now we're all familiar with the gravitational field. So here we have the ground, or the Earth, and if we